Okay. So from until last class, we reviewed the deep learning, right? And from this week, we will review the Pytorch library. So 이름이 뭐죠? 혹시 지금 들어온 학생? 강성군, 서군. 알겠습니다. Okay. So I mentioned in previous class, this slide is very important, right? To be implemented in the deep learning architecture, each individual layer should be differentiable, right? And differentiable means we need to get these two types of gradient, okay? The first one is the differentiation of the output with respect to its input. And the second one is the differentiation of output y respect to its parameter sector, right? We have to calculate these two gradients, and also to define these two gradients, the function have to be the forward rule, forward function have to be defined mathematically. Okay, so if forward rule is defined using these four basic operations plus multiplication, division, subtraction, then if you connect the variables, input variables using this kind of basic operation to output the y, then that layer is differentiable actually, okay? And the ultimate goal is to calculate this parameter update, okay? This is gradient descent formula, right? So from the sector, old sector, we need to update it. And to decide its direction, we need to calculate this DLD sector, where L is the loss, okay? And in Pytorch, actually, you can do this using two lines of code, okay? So that is these two, okay? Loss dot backward and optimizer dot stem, okay? So if you call this first function, loss dot backward, maybe you will see later, but I will say the conclusion first. If you call this function, then all of the DLD sector is calculated, okay? For all the parameters inside the deep learning architecture, you can calculate this DLD sector. That's what happens when you call this loss dot backward, okay? And then when you call the second function, optimizer dot step, actually the code calculates this, okay? You already obtained this, and this is the constant, and you already have all the parameters, right? After calling loss dot backward, for all the parameters, this DLD sector is calculated, and you call this function, then new parameters are calculated, okay? So this is what happens when you call these two lines of code, okay, in Pytorch. Okay. And another merit of, this is quite very simple, right? And another important thing you have to remember is, without the deep learning libraries, let's say your forward function looks like this, then you need to calculate by yourself. You need to calculate this manually, right? And have to implement this in the code, right? But the thing is, these gradients are dependent on the function itself, right? Depending on the forward function, the backward rule and parameter update rule always changes, right? And you have to define it in the code level, right? You have to define, so depending on which forward function you used, you have to differently define your backward and parameter update rule in the code level, right? Without the deep learning libraries such as Pytorch. Okay. But in the Pytorch, they automatically calculate this gradient, and actually they calculate this using some numerical method, okay, such as Newton method. Okay, so their backward function is not dependent on the forward function. Okay, right? So numerical method, they are providing some algorithm rather than this kind of closed form formula for gradient calculation, right? And that algorithm is same for all the forward function, okay? So you don't have to implement it differently for different forward functions, okay? That's another merit of the deep learning libraries such as Pytorch and TensorFlow, okay? So actually, this calculation is sometimes very hard. If the forward function is not that simple, calculating their gradient is also not trivial. But because of the gradient calculation is now done automatically, so you don't have to care about that anymore, okay? The thing you have to do is just calling this function, okay? If you call this function, then all the parameters, gradients are counted internally in the Pytorch library, okay? And I will explain how to implement this simple linear regression algorithm using the Pytorch library, okay, from now on. So I think you may know this linear regression algorithm. So given some X data, some scalar values as input, in the linear regression, it could be the vector could be also the input, but I'm illustrating where the inputs are also constant, having just one value, okay? And their y, let's say their y is also having just one value, right? Okay, so let's say this is some weight of a person, and this is height of a person. Okay, you can think of like this, right? Weight and height, they are somehow correlated, right? So we want to, so these blue points are some data point, right? Okay, so let's say there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 persons. We collected 10 persons' weight and height, okay, and visualize it in this 2D graph, right? And using this 10 persons data, we want to find some general function that can map weight to the height, okay? Given data, X and Y pairs, we want to learn some kind of function f, right, that can map X to Y. Okay, then if the new data comes, we can estimate their height. Okay, so that's our purpose here, right? And to solve this, to find function f from this X and Y pairs, there are a variety of ways, right? To solve linear regression, there are some ways, but we will solve this using gradient descent now, okay? And actually, that can be implemented like this, okay? So we first have to make some data. So please forget about the weight and height. I will arbitrarily make some data like 100 data. I will make 100 data and their ground, actually I will make it the data X and Y are having this relation, okay, in our example here, okay, and X is actually three-dimensional, having three-dimensional input. Sorry. X is having actually three-dimensional input, which is randomly initialized. We will first make 100 random X samples. And then this weight true, is defined as 1, 2, 3. Okay. And this B is initialized as 5. Okay. Then we can first make some X by randomly initializing it. And by multiplying this ground truth W and adding ground truth bias B, we can make this X and Y pairs. Okay. So this code are making the data, 100 data samples, okay, right? And this W and B are the weight we will find during our gradient descent algorithm, but it is randomly initialized, okay? Okay, this W true, B true are ground truths, W and B, right? And this X and Y are data obtained from using this W ground truth W and B. And we randomly initialize some W and B here. And we are expecting that this W and B are gradually close to this ground truth W true and B true. Okay, right? Okay. And this gamma is this. This is the gamma here, right? Gamma is initially set as 0.1. Okay, this is 0.1. And we will use one iteration for doing this gradient descent. Okay. Okay. So we first have to initialize our parameter. Our parameter sector is now constituted with W and B. So now we have to find W and B, which is initialized randomly, but eventually it have to be this W true and B true. Anyway, these WB are parameters we have to learn from the data, okay? Okay. We initialize it randomly. We initialize its value randomly, but its gradient, we have to make it, we have to initialize it as known, like here, okay? W is value itself, W dot grad, B dot grad, that's indicating the gradient value for that variables. And we have to initialize it as known, okay? And this is the forward rule in our function, okay? Okay. We will multiply W and add bias to our inputs. Okay. Okay. This is the forward rule, how to get the output from the input. Okay. And you can see those are composed of multiplication and addition, so they are differentiable. Okay. Anyway, we could obtain the output, and actually this is the loss, the distance between ground truth y and our prediction y on the matrix. Okay. We are measuring their distance. Okay. This is the loss. Okay. And we are meaning averaging by its dimension, and that's actually loss. Okay. And we will call loss dot backward. Okay. By calling this, for all the variables used, we can calculate their gradient. Okay. And then using this gradient descent, denoting this formula, we can update gradient for each parameters. Okay. And we will iterate it through 100 iteration. Okay. Then our parameter would be close to W true. Our parameters, which are W and B, they will be close to W true and B true. Okay. So everyone is understanding this. Okay. And this loss, we will accumulate losses for visualization purpose. Okay. Using this simple code, you can implement the linear regression. Okay, and you can optimize linear regressor using gradient descent algorithm. Okay. And this is the visualization for loss, actually. And this is the iteration. Okay. You can see their loss is gradually reduced, which means your network is outputting something which is close to ground truth. Okay. And this is visualization for obtained predicted W and B, and these are true B and true W. Okay, you can see those values are actually same, right? Okay. So this is the linear regressor. Okay. Maybe you are curious that how the loss function at this moment, I think you have to curious about how the loss knows where to backpropagate, where to backward. I mean, so when I said, when you call this loss dot backward, all the parameters, we can obtain the gradient, okay, right? But inside the, maybe somehow, maybe I'm expecting that you are not clear how they know which parameters they will calculate the gradient for, okay? Inside the Pytorch, if you make the variable, and when you connect those variables via this kind of operation, inside the Pytorch, these kind of graph structures are generated, okay? So maybe this is W, X, B, right? We will multiply this X and W, right? And add bias B later to output this Y on the pred, okay? And we will also connect this Y pred, actually this is Y pred. You will compare these two using this kind of operation again, right? And that will be actually the loss function, okay? then from the loss, it can know which variables are connected to it using this kind of graph structure. Okay. So from the backward, I mean from the rightmost side, there are loss function, right? From that, you can anyways backpropagate it like this until you meet the leftmost variable, right? Using the gradient calculation method I explained last time, gradients are gradually, step by step, calculated until it reaches the leftmost variable. Okay. So yeah, when you call this low step backward, you can think this kind of this kind of graph structures are generated when you connect variables using some formula. And when you call the low step backward function, the calculation, gradient calculation is step-by-step manner happened. You can think like that, okay? Okay. So are you clear about this? Okay. So in here, we don't have to care about how to calculate the gradient, okay? Right. Actually, we don't have to use any formula. We don't have to calculate any gradient by ourselves, right? But instead, we can just call this low step backward function. And also, if you call this b.data, you can print out some values stored in this variable b, okay? Actually, those are some randomly initialized values, right? From here, right? And you can also print out their gradient, corresponding gradient values. Those are DLDB, actually, right? This is DLDX, and this is DLDW, right? The differentiation of loss respect to itself, right? You can actually visualize it, print out by using this by accessing this variable, right? b.grad.data, okay? So, yeah. And you can implement this linear regressor like this, but Pytorch is providing more general styled code, okay? I will explain that, okay? So here, you have to specify some formula, okay, for connecting input X and parameters W and B, right? In this type of code, you have to specify by yourself, you have to initialize parameters, and also you have to, using formula, you have to connect input and parameters by yourself, okay? But actually, this type of formula is already implemented in the Pytorch as the torch.nn.linear operation, okay? And actually, you saw the input feature dimension was 3, right? And output dimension was 1 scalar value, okay? And you will also specify if these bias are used or not, okay? So if you check bias is equal to true, then you will add bias to the final output, unless just the function looks like this, okay? Anyway, this torch.linear is making the making the layer having this operation, okay? That's the net, okay? And this, by inputting just x as argument of this layer, you can predict y grid. Okay, in this style of code, you don't have to specify any formula. Okay, so the implementation becomes more easier using this method anyway. And also, this is the gradient descent formula, right? And before using that, you have to initialize the parameters by yourself. The same thing could be achieved by calling these two lines of the code. Okay. I said optimizer.step. When you call this, you can update each parameters, right? Okay. And so by calling this, you can do same thing as the left one. And also, instead of initializing variables by yourself, you can just call this optimizer.0_grad function. Then all the parameters inside the layers, they are initialized, okay? So if you have, like, this is simplified case, right? Having just two parameters, but let's say there are over 100 parameters, you have to waste your code by, you have to initialize that using 100 over 100 lines of code. Okay, that's wasteful. So, but instead, you can just initialize parameters by calling this one line of code. Okay, and also similarly, if your parameters are larger than this, you have to call the same form of the formula multiple times. That's wasteful. So anyway, instead you can just call this one line of the code. Okay, and before using this optimizer, you have to initialize it. And actually, multiple optimizers are already implemented in the Torch library. Okay, this is the implementation of gradient descent, stochastic gradient descent algorithm. Okay, and the thing you have to input is the epsilon. Okay, so I said there are one very small scale. Okay, so this epsilon can be set here by specifying it in here. This actually LR means learning rate, right? And we initialize it using some small values, meaning the epsilon here, right? So by specifying all the parameters inside the network we are training, right? Net.parameters, it has all the parameters we have to access. Actually, this net.parameters is having the list of all the parameters inside the network, right? And this LR is learning rate and is meaning this epsilon, okay? So by setting the optimizer for this sector and epsilon, the remaining information is the gradient only, the DL this sector. And that could be obtained from here, low step backward. And then after executing this line of code, we can update it like this, okay? So that's, yeah, anyway, the parameter, the Pytorch style code. Okay, and also we can further simplify the loss functions like this. So here you can see the loss function itself is formulated. We can see their formula actually, right? But in the right, this is the frequently called loss function, whose name is mean square error loss or L2 loss or some Euclidean distance loss. Okay, it has multiple names, and it frequently used when doing the regression task. Okay, so we define it actually as this torch.nn.msc loss function. Okay, so instead of directly implemented, we can define some MSC loss built in the Pytorch, and then we can call it like this. Okay, so this would be more convenient to implement, right? Their functions are same, but implementation becomes easier. Okay. And yeah, anyway, the results are same as before, okay? The Pytorch style code are easier to implement, but they are same in functions, okay? Okay, so this is the Pytorch style code for the training, okay? This is the data generation, and this is the definition for the network optimizer and loss function. And then using this line of code, you can train the network, okay? The thing you have to change is, depending on the application, maybe you have to change some network structure, right? And also you have to fit the dimension of the input and output, right? To do that, you have to manipulate the network structure. And also you have to adjust some of the learning rate, or you also have to change some optimizer depending on the application, okay? And depending on the application, you have to change the loss functions, okay? But except this, these training code are remained same, okay? You may see the same procedural code when using the Pytorch, okay? So that's anyway the merit for the Pytorch. You can simplify the training implementation, okay? That's actually the merit of the Pytorch or the TensorFlow, okay? And now you will see the merit more clearly by implementing this kind of more complex deep learning architectures, okay? Previously, we have just one layer. It was the linear regressor, right? But here, it is called as multi-layer perceptron. So its name, we frequently call it as MLP, okay? So inside the network, it has multiple linear layers, okay? This layer was called as the linear layer, right? And we have some activation function after linear layer and apply another linear layer and apply the nonlinear layer after that and apply another linear layer and apply another nonlinear layer, okay? This is the multi-layer perceptrons, okay? You can manipulate the number of layers. Actually, these have 3 linear layer and 3 nonlinear layer, right? But you can manipulate it depending on your application, okay? But thing is, why this kind of nonlinear layer have to be there? I will explain that. So, I mean, if you implement without this nonlinear layer, then the entire network
could be simplified like this. So plus like this. Okay, the entire formula could be simplified like this, and this becomes another linear layer, right? Even though you stacked multiple layers, but the actual functions becomes like the linear layer, right? So it only increases the complexity, but their ability to represent nonlinear uh, distribution of the data was loose. So to actually prevent your network to be like this, in the middle of the linear layers, this kind of non-linear layers are required. Okay, when constituting the multi-layer perceptron, you have to involve these non-linear layers. Okay, so this is saying the same thing. Okay, anyway, when you try to implement the MLP using Pytorch, you can actually feel that the only thing you have to change is this part, okay? The network structure only you can change, okay? Also, you have to maybe also change the data generation part, right? Anyway, but this line of the code for actually training the network is not changed, okay? Okay, and actually this part is also not changed, but this linear, nonlinear, linear, nonlinear, stacking multiple linear, nonlinear layers to constitute the MLPs are only changed, okay? So, and after training, when executing this code, you can obtain this line of graph, okay? Meaning that this is the iteration and this is the loss function, loss values. Okay, so when epochs goes, you can see the loss are indeed gradually reduced. Okay, and this is the visualization for the ground truth Y data, and this is the visualization for the predicted value from the MLPs. Okay, so this is the ground truth Y values, and this is the value obtained from the network. Okay, the ground truths were obtained like this, but anyway, the predicted values are obtained from the network output. So they are not that exactly same, but you can see the MLP network is anyway following the true Y values, right? Their formula is different. The original functions is the quadratic functions, right? But the network having the different operation, having some MLP layers, but it can mimic the original functions, okay? So this is kind of great thing, right? Okay. So, I mean, you can make the dim learning architecture and enforce it to mimic some arbitrary nonlinear functions. Okay, this is the merit of the dim learning. And I have to then explain the CNN architectures. Okay, this is meaning the convolutional neural network. Okay, this is one specific algorithms inside the deep learning method. Okay, but their operation is composed of the convolution, so that's why they are called as convolutional neural network. Okay, in between the image and the semantic labels, any differentiable layers could be here, right? We can locate any differentiable operations to constitute layers in between and could maybe train that, okay? But this convolution operation was frequently used for processing the 2D arrays, 2D images, okay? And is at the same time is differentiable, okay? So people try to involve this convolution operation to process the RGB images, okay? To map these RGB images to the semantic labels. The researchers are finding that this convolution operation is efficient. So after that, the CNN was proposed. Okay. Okay. And in CNN, the architectures are like this. So first part are composed of convolution and pooling and nonlinear operation. And the later part, they are composed of linear layer and some of nonlinear layers. Okay. This is actually similar to MLPs. That processes the 1D signal, one-dimensional signal, right? And the first part, they are dealing with two-dimensional signal, right? And after applying the convolutions, actually the dimension, 2D signals are reduced. Their dimension is reduced. And after a while, the flattening is occurs. So it makes the 2D signals to the one-dimensional vector. Okay, this is called as flattening. And then we apply the MLP operation, which is the operation for processing the 1D signal. Okay, and every layers are differentiable. Okay, so the combination of differentiable layers that becomes another huge differentiable architecture. Okay, so we could train their parameters. Okay, so and the first part they are called as convolutional layers. They are more dedicated to capture some low-level features, and then it maps it to the semantic label via these fully connected layers. Okay, its architectures are quite similar to MLP, but they are called as fully connected layers inside the CNN architecture. Okay. Okay. And I will show you how we can implement the CNN architecture inside the Pytorch library. Okay. You have to define some class. Okay. Actually, this is easy things. You can implement some architecture inside the Pytorch. And you have to name it like this, okay? And then here, it's similar to the constructor in the OP, okay? These constructors are once called when network instance is initialized, okay? So normally we implement some of the layers here, okay? And this, you will define the forward function of that network, okay? And also, maybe you need backward and parameter update method if you are not using Pytorch library. But because you are using the Pytorch library, this backward and parameter update rule is inherited from the superclass of the Pytorch, and they are already implemented as the some numerical gradient calculation method. Okay, and also I mentioned before they are not dependent on the forward function. So yeah, once they are implemented, we do not have to change it depending on the depending on the forward function, right? They are independent to this forward function. So we can just inherit that from the superclass. And when implementing for specific network architecture, we don't have to implement it further, okay? We can only implement the forward function. Okay. So this is the CNN architecture having multiple convolutional layers. Actually, this NN sequential is meaning that stacking multiple layers inside the argument. Okay, so they are stacking this number of layers, all are differentiable, right? And then you will stack the linear layers. This is the fully connected layer, and this is the convolutional layers. Okay. So this kind of definition could be once executed when the instance is generated. So we can implement it in the constructor. Okay. And for the forward function, you have to specify how signals are propagated from the input to the output. So given X, you will first apply the convolutional layer to output the middle output. And actually, this is the flattening operation, reshaping from 2D signal to the one-dimensional vector. And then you will input the one-dimensional vector to the fully connected layer to get the final output and return it. So this is the forward function, right? Okay. And using the same line of the code, but initializing your network using this class, you can implement the CNN training code. Okay. So except for this net and this class definition, everything are same as before when implementing the MLP or linear regressor, right? That's actually the merit of the Pytorch. And then I will explain you how we can implement some classification network, okay? Image classification, as I told you before, is classifying the image data X towards its semantic label Y, okay? We are assuming that images are composed of one main object. So for example, this first line is having airplane as the main object. Second row is having automobile as the main object, and so on. So we will classify these images according to its main object class. Okay, that's the image classification task. Okay, and also in this MNIST dataset, there are 10 classes denoting the digits from 0 to 9. We want to classify the images. Okay, this is another examples for the image classification dataset. Okay, and so we will tackle this image classification task, and I will show you how we can train the network for this image classification task using the Pytorch code, okay? But before that, I want to explain you how we can first implement the binary classification task, okay? So in the binary classification task, there are only two labels, 0 and 1. The X input need to be classified to 0 and 1 class, okay? This is the binary classification, and actually the algorithm, the primitive algorithm that conduct this binary classification is called as the logistic regression, okay? What they do is their layers, network structures looks like this, okay? So they output some Z output value from the X, okay? And first, they multiply the linear layer for the input X, okay? And then they apply the sigmoid function, okay? And this is actually the sigmoid function, and you can see from using this sigmoid function, the X input value ranges from -infinity to infinity. It goes towards some value, output value between 0 and 1. Okay, this is the sigmoid function. So when you use the sigmoid function, this no matter how big or how small these values are, it can map the output to the 0, 1 values. Okay. Okay. And then so logistic regressor is finding Z, which is between 0 and 1. Okay. And then you will threshold it by 0.5. And if the Z is larger than or equal to 0.5, then you can say the class is 1. And if the Z is less than 0.5, then you can say the class is 0. Okay. So using this continuous value, whose range is from 0 to 1, you can threshold it by 0.5 and then achieve this binary classification. Okay. This is what happens inside the logistic regression. Okay. Even though its name is regression, what it actually does is classification. Okay. And this is the binary cross entropy loss. People are saying this as the BCE loss frequently, which is used to train this logistic regression. Okay, and first you have to know that these two lines of the loss functions are same, and they are all denoting the BCE loss. Okay, so this YN is the ground truth label. And this Gn is the output of the linear regression method. So G is denoting the output of the linear regressor, and Y is ground truth label for nth data. Okay. And when Yn is equal to 1, its loss is this. And when Yn is equal to 0, the loss functions are like this. That's what this line is denoting. And actually that's samely represented like this. So when Yn is 1, then this becomes 0. Okay. The entire term becomes 0, right? And when this is 0, this goes 0, and this becomes 1, right? So you can think that, I mean, when Yn is equal to 1, these are same as this multiplied by minus, and this entire term goes to 0, right? We can ignore this, right? But inversely, when Yn is equal to 0, this goes 0, and this actually goes 1, and this term only remains, and that's actually same as this. Okay, so the upper, this formula and this formula are actually same. You have to notice that. And then I will show you how this function works. Okay, so when ground truth is 1, this Gn should go 1, right? Our output should follow the ground truth value. Okay, and when Yn, the ground truth is 0, our Z should go to 0. Okay, that's what we want for during the training, right? And then we will draw this graph. Okay, the log Zn is this, but minus log Zn, that looks like this. Okay, and Zn, this point is 1, 0, right? When when the Z value is 1, the log Z is 0. So this point is 1, 0. And you have to notice that this Gn is belonging to this range because it is obtained from the sigmoid function, right? Its value is limited between these, okay? And we have to minimize this loss function, okay, for these values of G, okay? Then the minimum value we can obtain is this point, okay? I mean, interruption. So in this value, their y value is kind of large. This for these values of z, this is relatively reduced but still large in scale. But for this z, this minus log z is minimized. Okay, so actually minimizing this loss is actually equivalent to making this Gn close to 1, okay? So by minimizing this, we are actually achieving this. We can making this Gn goes towards 1, okay? And when you draw the graph for this, okay, you can also get the same result. But anyway, I will briefly explain that. So anyway, this 1 minus Gn needs to be in this range, okay? And to minimize this needs to be, we have to make this goes to 1, right? And making this term go to 1 is equivalent to making Zn goes to 0, right? So when Yn ground truth is 0, we will minimize this. And that is actually same as making Zn goes to 0, okay? So using this binary cross entropy laws, we can achieve what we want, okay? So for the samples whose ground truth is 0, we want to make that output goes to 0, close to 0. And for the samples whose ground truth is 1, we want to make its output G close to 1, okay? And then we will threshold its value by 0.5. And if the value is larger than 0.5, we will regard it as class 1 sample. And if its Z value is less than 0.5, then we will regard it as the class 0 sample, okay? That's the binary classification, okay? And you can implement it using the Pytorch code like this. So this is the BCE laws, okay? And you can see that the same codes are used. And these are the logistic regressor, okay? But when using these BCE laws, you have to apply after this linear regression, linear layer, you have to apply sigmoid function by yourself, okay? And then the loss functions are used. The BCE loss is applied and backward, and step is called to update the parameters, right? But when you use this with logis loss, inside the loss function, the sigmoid is implemented as well. So after the linear layer, without calling this sigmoid, you can directly call this loss function. So this BCE with logit, it first call the sigmoid function and then apply the BCE loss. So you don't have to implement it by yourself. Okay, so that's small difference. And this is showing that actually two losses are doing the same thing. Okay. Okay, and then next class, I will explain about the multi-class classification task. Okay. Okay, I finished today's lecture here. Thanks a lot.